Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC, and in the second question, we will find out the area of rectangle ABCD that blocks this circle. So we'll start with the first question. In the drawing, actually we'll answer the first question in two different methods. So we'll start with the first method. In the drawing, we have triangle ABC, side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is inscribed by this triangle, triangle ABC. Okay, so we'll start with the first method, and we will do a construction. From point C, we will draw perpendicular on AB. Repeat again, from point C, we will draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Okay, we will define the touching point of the perpendicular from point C and AB as D. And we will focus on the right triangle, triangle BDC. Okay, so actually I will copy the right triangle, triangle BDC in a new page, and we will analyze triangle BDC. This is the right triangle, triangle BDC that I copied from the original drawing. We know that the sum of the angles in the right triangle, triangle BDC must be equal to 180 degrees. So which angles we have in triangle BDC? We have this angle that is equal to 60 degrees, plus this angle that is equal to 90 degrees, plus this angle that is a missing angle. So we define the missing angle as x. So the sum of those three angles, in total they must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here we have 60 degrees plus 50 degrees is 150 degrees, plus x equals to 180 degrees. Here we subtract 150 degrees from this equation, and we'll get that the missing angle x is equal to 180 degrees minus 150 degrees. It is equal to 30 degrees. So this angle equals to 30 degrees. So we continue to focus on the right triangle, triangle BDC. In the right triangle, triangle BDC, we know that sinus 30 degrees sinus 30 degrees is equal to BD over BC. Okay, so sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2, and it is equal to BD over BC, but BC equals to 2 units, so we substitute BC by 2. We'll multiply this equation by 2 and we'll get that BD equals to 1 unit. So BD equals to 1 unit. Here we can write in the drawing itself, the original drawing, that BD equals to 1 unit. And we also know, we continue to focus on the right triangle, triangle BDC. So in the right triangle, triangle BDC, cosine 30 degrees is equal to DC over BC. Okay, and cosine 30 degrees is square root of 3 over 2, and it is equal to DC over BC, and BC equals to 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. Here we'll multiply this equation by 2 and we'll get that DC equals to square root of 3 units. DC equals to square root of 3 units. If DC equals to square root of 3 units, so you can write here that DC equals to square root of 3 units. So here we know that this angle equals to 30 degrees. Angle BCA equals to 75 degrees. Angle DCB equals to 30 degrees. Therefore, if we subtract angle ACB from angle DCB, we'll get this angle, angle DCA. So here angle ACB equals to 75 degrees, angle DCB equals to 30 degrees. 75 degrees minus 30 degrees equals to 45 degrees. Okay, we found out that this angle equals to 45 degrees. In the next step, we'll focus on the right triangle, triangle ADC. So I'll copy the right triangle, triangle ADC in a new page and we'll analyze triangle ADC. Okay, so here we have side DC, angle ADC is 90 degrees. Angle ACD, this angle is 45 degrees. So actually, this is the right triangle, triangle ADC. That I copied from the original drawing. In the right triangle, triangle ADC, we know that the sum of the angles must be equal to 180 degrees, so we'll define the missing angle as X. So here, which angles we have in the right triangle ACD? this angle equals to 45 degrees, plus this angle is equal to 90 degrees, plus this angle that is equal to x. In total, they must be equal to 180 degrees. 45 degrees plus 90 degrees is 135 degrees. And you know that 135 degrees plus x must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that angle x, the missing angle x equals to 180 degrees minus 135 degrees is 45 degrees. So we found out that this angle equals to 45 degrees. So actually, in triangle ADC, we have two angles that are equal to each other. Those two angles that are equal to each other, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So here, actually, in front of this angle, we have side AD. In front of this angle, we have side DC. And according to the rule that I mentioned, those two sides must be equal to each other because they are located in front of equal angles. But here, we have already found out that DC equals to square root of 3 units. So we can write here that DC equals to square root of 3 units. And from this equation, AD equals to DC equals to square root of 3 units. You will derive that AD is also equals to square root of 3 units. Okay, AD is also equals to square root of 3 units. So you can write here that AD equals to square root of 3 units. So in the next step, we will implement the Pythagoras theorem on the right triangle, triangle ADC. Okay, according to the Pythagoras theorem, so I'll copy again the right triangle, triangle ADC, and we'll implement the Pythagoras theorem on the right triangle, triangle ADC. So this is the right triangle, triangle ADC that I copied from the original drawing. So in the right triangle, triangle ADC, by PT is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say, AD squared plus DC squared equals to AC squared. Okay. Here AD equals to square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC also equals to square root of 3, therefore DC squared is square root of 3, that is also 3, it is equal to AC squared. So in conclusion, I found out that AC squared is equal to 3 plus 3 is 6. Here we take a root out of this equation, equation number 1, and we get that according to equation number 1, AC equals to the square root of 6 units. AC equals to the square root of 6 units. Now we have all the sides of triangle ABC. We'll use a special formula in order to find out the radius of this circle that is described by this triangle ABC. Actually, we have a rule that whenever a circle is described by a triangle, here this circle is described by triangle ABC, then the radius of this circle that is described by triangle ABC will be equal to the area of triangle ABC. This is the sign for the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. So what is the semi-perimeter? The semi-perimeter, the definition of a semi-perimeter is the perimeter over 2. And the perimeter of triangle ABC equals to the sum of the sides of its length, the sum of the side lengths of triangle ABC, that is A. Here side AB equals to A units in its length, side BC equals to C units in its length, and side AC equals to B units in its length. Therefore, the sum of the side lengths of triangle ABC is A plus B plus C, and if we divide it by 2, we'll get the semi-perimeter of triangle ABC. So the area over the semi-perimeter of triangle ABC will be equal to the radius of this circle that is inscribed by triangle ABC. So we use this formula in order to find out the radius of this circle that we are looking for. So according to the formula, that the radius of the circle equals to the area of triangle ABC over the semi-perimeter of the triangle ABC. So what is the area of triangle ABC? Actually, the area of any triangle is equal to the base of the triangle times the height to the base over 2. Repeat again, the area of any triangle equals to the base of the triangle times the height to the base over 2. So here we use this formula in order to find out the area of this triangle ABC. So the area of the triangle ABC will be equal to the base, so we'll take the base as AB, the base is AB, the height to the base is CD. Why CD is the height to the base? Because it's creates 90 degrees with the base. So the height is CD over 2. I'll repeat again, the area of this specific triangle ABC equals to the base is AB times the height to the base is CD over 2. Okay, so here the area of triangle ABC, is equal to AB equals to BD plus AD. That is to say, AB equals to 1 plus square root of 3 units times CD. We already found out that CD equals to square root of 3 units. So it is, we substitute CD by square root of 3 over 2. So in conclusion, we found out that the area of triangle ABC equals to 1 plus square root of 3 times square root of 3 over 2. That is to say, the area of triangle ABC is equal to 1 times square root of 3 square root of 3, and square root of 3 times square root of 3 is 3, so it is square root of 3 plus 3 over 2. And here square root of 3 is 1.732 plus 3 over 2. So here 1.732 plus 3 is 4.732 over 2, and here 4.732 over 2, it is equal to 2.366 square units. So the area of triangle ABC, this is the sign of the area of triangle ABC. It is equal to 2.366 square units. And what is the semi-perimeter of triangle ABC? The semi-perimeter is the perimeter over 2. So the perimeter is AB plus BC plus AC, and if we divide the perimeter by 2, we'll get the semi-perimeter. So here we'll get that AB is 1 plus square root of 3 plus BC is 2 plus AC is square root of 6 over 2. So in conclusion, we found out that the semi-perimeter of triangle ABC S is equal to 1 plus 2 is 3, 3 plus square root of 6 plus square root of 3 over 2. So here S equals to square root of 6 plus square root of 3 plus 3 over 2 is equal to 3.59 units. 3.59 units. So the area, the radius of the circle, according to the new formula that I presented to you, will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC is 2.366 square units, and the semi-perimeter of triangle ABC is 3.59 units. So here the result will be 2.366 over 3.59 equals to 0.6589 units. So the answer to the question is that the radius of this circle that is inscribed by triangle ABC is equal to 0.6589 units. We finish with the first method. In the next step, we'll find out the radius of this circle that is inscribed by triangle ABC according to the second method. Okay. In the second method, we will define the center of this circle as point O. We will define the point of tendency of tangent BC with this circle as point D. We will join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself, therefore OD is the radius of the circle, so we define the radius of the circle as R. And we have here rule number 1, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. The radius OM, it is drawn to point M, that is the point of tendency, therefore tangent AB will be perpendicular to the radius MO. We implement rule number 1 in our drawing. Here we have the radius OD that is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. So if BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, we join points O and V together by a straight line. We join points O and C together by a straight line. We define the point of tendency of tangent AB with this circle as point E. We will join points O and D together by a straight line. Point O is the center of the circle. Point E is the point of the circle itself, therefore OE is the radius of this circle, that is equal to R. Here we have the radius OE that is drawn to the point of tendency, that is to say it is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. So if AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We define the point of tendency of tangent AC with this circle as point F. We'll join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself. Therefore, OF is the radius of the circle, that is equal to R. And again, we have the radius OF that is drawn to the point of tendency, that is to say it is drawn to point F, that is the point of tendency of tangent AC with this circle. And whenever we have a radius that is drawn to the point of tendency, then AC will be perpendicular to FO. That is to say, this angle will be equal to 90 degrees according to rule number 1, and this angle will be also equal to 90 degrees according to rule number 1. Okay, and we also have here rule number 2 that states that the lengths of two tangents from a common external point to a circle are equal. So here we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA, and tangent PB. And according to rule number 2, the lengths of those two tangents, that is to say PA and PB, are equal to each other. That is to say PA equals to PB. So whenever you draw two tangents to a circle from a common external point of that circle, in this example is from point P is the common external point, then the lengths of those two tangents will be equal to each other. That is to say PA will be equal to PB. Okay, so here we have from the common external point, point B, we have two tangents to this circle, tangent BE and tangent BD, and according to rule number 2, the lengths of those two tangents must be equal to each other. That is to say, BD equals to EB. Likewise, if you focus on the current standpoint point C, from the current standpoint point C, we have two tangents to the circle, tangent CD and tangent CF. And according to rule number 2, the lengths of those two tangents must be equal to each other. That is to say, CF equals to DC. Okay, so in the next step, we will prove that the green triangle BOD is congruent to the orange triangle EBO. So why the green triangle is congruent to the orange triangle? So here we write it down. We have triangle BDO, the green triangle, and the orange triangle BOE. Why those two triangles can go into each other? First of all, we just right now found out that BD equals to BE. BD equals to BE. Okay, here. BD equals to BE according to rule number 2. In addition, we have EO that is equal to R equals to DO. They are equal to each other because both of them are the radii of the circle. This is equal to R. So EO equals to DO equals to R. And finally, BO is a common side that belongs to both triangles, so BO equals to itself. BO equals to BO. So we actually proved that the green triangle BOD is congruent to the orange triangle BOE according to angle similarity rule. And from the fact that those two triangles, that the green triangle is congruent to the orange triangle, we conclude that those two angles are equal to each other. Here, those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles must be equal to each other. That is to say, angle OBD in the green triangle must be equal to angle OBE in the orange triangle. Angle OBD equals to angle OBE. Okay, angle OBD equals to angle OBE. So if we define one angle as alpha, if we define angle OBE as alpha, then from this equation we derive that the angle OBD is also equal to alpha. Angle OBD is also equal to alpha. So both those two angles are equal to alpha, therefore we can write down that alpha plus alpha equals to 60 degrees. It is equal to 60 degrees according to what is given us the question. Alpha plus alpha is 2 alpha equals to 60 degrees. We divide this equation by 2 and we get that angle alpha equals to 30 degrees. Okay, so here I found out that angle alpha equals to 30 degrees. This angle alpha equals to 30 degrees, and this angle alpha also equals to 30 degrees. So we will focus on the yellow triangle ODC, and on the pink triangle COF. Actually, those two triangles also can go into each other according to side rule, so I prove it quickly. According to exactly the same rules, so I write it down, the yellow triangle DOC, and the pink triangle OFC. Okay. So why those two triangles can go into each other? First of all, according to rule number 2, BC equals to it is DC that is equal to FC according to rule number 2. The lengths of two tangents from a common external point to a circle are equal. Repeat again. BC equals to FC according to rule number 2. In addition, we have here the radius DO is equal to the radius OF. Okay, here DO is equal to OF. They are both the radii of the circle, therefore they are equal to each other. And finally, we have side OC is a common side, so side OC equals to itself. It's a common side that belongs to both triangles. Okay, OC equals to OC is a common side. Therefore, we proved that those two triangles can go into each other. Triangle OSC, the yellow triangle ODC, is congruent to the pink triangle OFC according to side rule. Okay, the two triangles can go to each other according to side rule, and from the fact that the two triangles can go into each other, we will derive that here those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So here angle FCO, this angle is equal to this angle that is actually angle OCD. Repeat again. Angle FCO equals to angle OCD according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define one angle as theta, if angle OCD equals to theta, then from this equation we derive that angle FCO is also equals to theta. So both those two angles are equal to theta according to our definition, and according to what is given as the equation, the sum of those two equal angles, that is to say theta plus theta, equals to 75 degrees. It is given as the equation. So you can write down that theta plus theta equals to 75 degrees. That is to say 2 theta equals to 75 degrees. We'll divide this equation by 2 and we get that angle theta equals to 75 degrees over 2 is 37.5 degrees. So we found out that angle theta equals to 37.5 degrees. We can write here that angle theta equals to 37.5 degrees. And then also angle theta equals to 37.5 degrees. Okay. In the next step, we'll focus on the green triangle OBD. In the green triangle OBD, according to, actually here, the value of tangents 30 degrees is very easy to say from the drawing that tangents 30 degrees is equal to OD over BD. Okay, I repeat again. In the green right triangle OBD, tangents 30 degrees equals to OD over BD. But here OD equals to R, it is the radius of the circle, over BD. So in conclusion, I found out that tangents 30 degrees equals to R over BD. Tangents 30 degrees equals to R over BD. Here we'll multiply this equation by BD and then we'll divide it by tangents 30 degrees and we'll get that BD equals to R over tangents 30 degrees. Okay, we found out that BD equals to R over tangents 30 degrees. We repeat on the same process on the yellow triangle ODC. On the yellow triangle ODC, it's very easy to see from the drawing that tangents 37.5 degrees is equal to OD over DC. I'll repeat again, in the yellow triangle ODC, tangents 37.5 degrees equals to OD over DC. Here OD equals to R, so we'll substitute OD by R, and DC is the missing variable. So in conclusion, we found out that tangents 37.5 degrees, it is equal to R over DC, tangents 37.5 degrees equals to R over DC. Here we will multiply this equation by DC and then we'll divide it by tangents 37.5 degrees and we'll get that the value of DC is actually equals to R over tangents 37.5 degrees. Okay, so here we actually found out the values. We found out the values of BD and DC. But actually, it is given us the question that BC equals to 2 units. And you can see from the drawing that BC equals to BD plus DC. Okay, BC equals to BD plus DC. Okay, it is very easy to see from the drawing that BC equals to BD plus DC. That is to say, BC equals to BD, that is R over tangent 30 degrees, plus DC, that is actually R over tangent 37.5 degrees. Okay, yeah. So here we'll calculate the values of 1 over tangent 30 degrees. We calculate the value of 1 over tangent 37.5 degrees, and this way we'll get out the value of R. But before that, we take R as a common factor, and we get that BC is equal to R, 1 over tangent 30 degrees, plus 1 over tangent 37.5 degrees. Okay, we found out that BC equals to, here we took R as a common factor, and we got that is equal to this expression. Now we calculate the values of each expression. We will add them together, and then we will divide BC by the value that we get here, and in this way we find out the radius of the circle that we are looking for. So here tangents 30 degrees is equal to 0.57735, and 1 over tangents 30 degrees, it is equal to 1.732 units. So BC equals to R, 1.73205 units, plus 1 over tangent 37.5 degrees. Actually 37.5, the tangent of 37.5 degrees is 0.767, and 1 over tangent 37.5 degrees, it is equal to 1.303. And if we add the two numbers together, we get that BC equals to R, and 1.73205 plus 1.303 plus 1.73205. In total, it is equal to 3.0352 units. We know that BC equals to 2. So here we found out that R, here we will divide this equation by 3 over, we divide this equation by 3.0352, and we get that R equals to 2 over 3.0352. And we get that the result is 0.6589 units. So repeat again, the radius of the circle that we are looking for equals to 0.6589 units, exactly as we received in the first method. Okay, we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in two different methods. Okay. In the drawing, we have rectangle ABCD. Inside the rectangle, we have a circle. Actually, the circle is blocked by the rectangle, or the circle is described by rectangle ABCD. We also know that chord SP, this is chord SP, is equal to 6 units in its length. Line segment SQ is equal to 5 units, and our mission is to find out the area of this rectangle ABCD. We start with the first method. We define the center of this circle as point O. Here, point O is the center of the circle. But before that, we know that all the angles inside the rectangle are right angles, so those angles, they are all equal to 90 degrees, they are right angles. And we will define side AB of the rectangle as A. We will define side BC, the width of the rectangle as B. It is very easy to prove that the width of this rectangle is also the diameter of the circle. So I write down that BC also equals to the diameter of the circle. And here we will join points O and P together by a straight line. So point O is the center of the circle. Point P is the point of the circle itself. This is exactly the definition of a radius. So OP is the radius of this circle. We'll define the radius of this circle as R, therefore OP equals to R. And I've already mentioned that the diameter of the circle equals to B, therefore the radius will be equal to B over 2. That is half of the diameter. So here we have P is the point of tendency of tangent BC with this circle, point of tendency, and we have the radius of P that is drawn to the point of tendency. Therefore, whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius O, or PO. So VC is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Okay? We define the point of tendency of tangent DC with this circle as point F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point of the circle itself. Therefore, OF is the radius of this circle that is equal to R. Again, F is the point of tendency of tangent DC with this circle. We have the radius OF that is known to the point of tendency. Therefore, tangent DC will be perpendicular to the radius FO. That is to say, this angle equals to 90 degrees according to rule number 1, and this angle also equals to 90 degrees according to rule number 1. So here we have we created here quadrilateral OPCF. Inside quadrilateral OPCF we have 1, 2, 3 right angles. Whenever you have a quadrilateral with three right angles, the fourth angle must be equal to 90 degrees. Also, why? Because of the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So this angle must be also equal to 90 degrees. It is a right angle. And here we have rule number 4. According to rule number 4, the perpendicular from the center of a circle to a chord bisects the chord. So here we have the center of the circle is point O. From point O, we draw the perpendicular OM on chord CD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. And according to rule number 4, this perpendicular OM bisects chord CD. That is to say, CM equals to MD. CM equals to MD. Why? Because the perpendicular OM bisects the chord CD. That is to say, divide this to 2 equal parts. Therefore, CM equals to MD. We will implement rule number 4 in our drawing. Here, from the center of this circle, that is point O, we'll draw perpendicular on chord SP. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point O and SP as M, and according to rule number 4, the perpendicular OM bisects the chord SP. That is to say, divide this, divides chord SP into 2 equal parts, or SM equals to MP. So if SM equals to X, it means that MP must be also equal to X, because it divides it into 2 equal parts. Okay? So we can write down that here that SM plus MP is x plus x, that is 2x. That is to say 2x equals to SP. SP equals to 2x, it is very easy to see it from the drawing. SM plus MP is x plus x, that is SP. Okay, so here 2x equals to SP. But according to what is given as the question, SP equals to 6. So let's substitute SP by 6. And from this equation, we derive that 2x equals to 6. Okay, 2x equals to 6. We divide this equation by 2 and we get that x equals to 3. X equals to 3. X equals to 3. Here also x equals to 3. X is actually MP. And MP equals to 3 units. In the next step, from point Q, we draw perpendicular on BC. Again, from point Q, this point, we draw perpendicular on BC. So here, so actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as H. By drawing this perpendicular, we created the quadrilateral, so we define the intersection point between the perpendicular QH and the radius QF as G. Okay, so by drawing this perpendicular QH, we created the quadrilateral QPGH. In quadrilateral QPGH, we have 1, 2, 3 right angles. Again, in quadrilateral QPGH, we have 1, 2, 3 right angles. So if we have 3 right angles, the fourth angle must be also a right angle. This angle, in order to complete the sum of the angles in quadrilateral QPGH to 360 degrees, this angle must be also equal to 90 degrees. So in quadrilateral QPGH we have 4 right angles, therefore it must be this left angle if not a square, so we relate to quadrilateral OPGH as a rectangle. Quadrilateral OPGH is a rectangle. Why? Because it has 4 right angles. Repeat again. Quadrilateral OPGH is a rectangle. And we also have the rule that the opposite sides of a rectangle are parallel to each other. That is to say, side OP is parallel to side GH. OP is parallel to GH. Repeat again. According to the rule that the opposite sides of a rectangle are parallel to each other, we get that side OP is parallel to side GH. But here, GH is part of the perpendicular QH. Okay, repeat again. G edge is part of the perpendicular Q edge. Q edge is a perpendicular. It must be a straight line. We write it down that Q edge is a straight line. It's a perpendicular. Q edge is a straight line. And repeat again. Q edge is a perpendicular. It is absolutely a straight line. And we know that part of the straight line Q edge is parallel to OP. So if part of a straight line is parallel to another straight line, the straight line itself must be also parallel to the other straight line, to the other straight line. Okay? So here, the straight line QH must be also parallel to the straight line OP. QH is parallel to OP, because if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Okay? Therefore, we actually found out that QH, the straight line QH, is parallel to OP. Okay? QH is parallel to OP, and we have the rule that alternating angles between parallel lines are equal to each other. Here, those two angles are defined as alternating angles because of the fact that they are located between the parallel lines OP and QH. So here, angle OPQ, this angle, is equal to this angle, that is actually angle PQH. PQH. Those two alternating angles are equal to each other because they are located between the parallel lines OP and QH. So if we define one angle as theta, if angle PQH equals to theta, then from this equation we get that angle OPQ is also equal to theta. Therefore, those two angles, they are both equal to theta according to our definition. Here, this angle equals to theta according to our definition. In the next step, we will focus on quadrilateral QHCD. Inside quadrilateral QHCD, we have 1, 2, 3 right angles. Again, inside quadrilateral QHCD, we have 1, 2, 3 right angles, and therefore the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in this quadrilateral, in this quadrilateral to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral QDHC, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral QHDC. Here, this quadrilateral QHDC is a rectangle. Why? Because it has 4 right angles. So here, quadrilateral QHDC is a rectangle. Okay. So, but we know that the opposite sides of a rectangle are equal to each other. That is to say, QH is equal to DC. In rectangle QH DC, QH must be equal to DC. Rectangle QH DC, QH must be equal to DC. But DC is the opposite side of AB in rectangle ABCD. Again, DC is the opposite sides of AB in rectangle ABCD, and we know that the opposite sides of a rectangle are equal to each other. That is to say, DC equals to AB. DC equals to AB. And from this equation, QH equals to DC equals to AB, we will derive that QH is equal to AB. Okay, QH equals to AB. But according to our definition, AB equals to A here. AB equals to A according to our definition. So we can write down that AB equals to A. And from this equation, QH equals to AB equals to A, we will derive that QH is also equals to A. Here, QH is also equals to A. QH is also equals to A. Okay, QH equals to A. So can I feel that QH equals to A? Okay, QH equals to A. In the next step, we will focus on the green small right triangle, triangle OMP. I will copy triangle OMP in this new page and we will analyze triangle OMP. Okay. So actually this is the right triangle OMP. This is the copied from the original drawing. And here, what is the value of cosine theta? The value of cosine theta is MP over OP. So I write it down. Cosine theta is the right triangle OMP. Cosine theta equals to MP over OP. But MP equals to 3 units, so we substitute MP by 3. And OP equals to B over 2. So we substitute OP by B over 2. Here we'll move 2 to the numerator and B to the denominator, and we get that 2 times 3 is 6 over B. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. Okay? Cosine theta equals to 6 over B according to equation number 1. Here we'll focus on the big right triangle, triangle QPH. In the big right triangle, triangle QPH, what is the value of cosine theta? Triangle QPH the right big triangle, triangle QPH. In the right big triangle, triangle QPH, cosine theta equals to QH over QP. I repeat again, in the big right triangle, triangle QPH, cosine theta equals to QH over QP. We have already found out that QH equals to A, so we substitute QH by A. What is the value of QP? It is very easy to see from the drawing that QP equals to 5 plus 6. SP equals to 6, so it is 5 plus 6, that is 11. QP equals to 11, so we substitute QP by 11. Okay, so here I found out that according to equation number 2, cosine theta equals to A over 11, so I write it down. We found out that cosine theta equals to A over 11 according to equation number 2. But here, according to equation number 1, we have already found out that cosine theta equals to 6 over B. So we have two different expressions for cosine theta. Therefore, we create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Here cosine theta according to equation number 1 equals to 6 over B, and it must be equal to cosine theta according to equation number 2, that is equal to A over 11. So I found out that according to equation number 3, 6 over B equals to A over 11. Here we cross multiply this equation, equation number 3, and we get that according to equation number 3, A times B equals to 6 times 11 is 66. According to our definition, AB equals to A and BC equals to B. And the area of any triangle, and especially triangle ABCD, equals to the length of the triangle times the height. The length is AB, the length times the width. The length is AB, the width of triangle ABCD is BC. And we have already found, according to our definition, AB equals to A and BC equals to B. And we just right now found out that A times B is 66, so here AB is 66. So in conclusion, we found out that the area of the rectangle ABCD that we are looking for is equal to 66 square units. 66 square units. Okay, here the area of this rectangle ABCD equals to 66 square units. We finished with the first method. In the next step, I present to you how to find out the area of this rectangle ABCD using the second method. Okay. In the second method, we define the center of this circle is point O. And as we already did in the first method, we define the length of the side AB as A. We define the width of the rectangle ABCD BC as B. As I already mentioned in the first method, BC is also the diameter of the circle, so I write it down. We know that all the angles inside a rectangle are right angles. So here all the angles are equal to 90 degrees. We join points O and P together by a straight line. I don't want to repeat on the same process. We have already, according to rule number 1, here this angle equals to 90 degrees and this angle equals to 90 degrees according to the rule that a tangent to a circle is perpendicular to the radius to its point of tendency. O is the center of the circle, P is the point of the circle itself, therefore OP is the radius of this circle. But we know that the diameter is B. If the diameter is B, then the radius must be equal to half of it, that is B over 2. Here we will extend PO by a straight line until it intersects with side AD. So here we define the touching point of the extended PO and side AD as F. In rectangle and in quadrilateral FPDC we have 1, 2, 3 right angles. Okay, we have 3 right angles, therefore the fourth angle must be also a right angle. Here this angle must be a right angle according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Likewise, in quadrilateral ABFP we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees according to the same rule. Okay. We define this point as point L. What is the definition of LP? Chord LP passes through the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. So here LP is the diameter of the circle, and I already mentioned that the diameter of the circle equals to B. Here we join points N and L and S together by a straight line. By joining points L and S together by a straight line, we created peripheral angle LSP. LSP is a peripheral angle, and the peripheral angle LSP rests on the diameter of the circle, that is LP. And we actually have a rule that relates to, rule number 5 relates to a peripheral angle that rests on the diameter of the circle. Here, peripheral angle A and B rests on AB, that is the diameter of the circle. And according to rule number 3 and rule number 5, any peripheral angle that rests on the diameter of the circle is equal to 90 degrees. So angle A and B equals to 90 degrees. Why? Because it rests on the diameter of the circle. Okay? According to rule number 5, we get that the peripheral angle LSB must be equal to 90 degrees. So this angle equals to 90 degrees. Okay? And here we have what is the length of FP. We already proved that ABFP is a rectangle because it has 4 right angles. So rectangle ABPF, its opposite sides are equal to each other. That is to say, side AB equal to side FP. But according to our definition, side AB equals to A. Here AB equals to A. And if AB equals to A and the opposite sides of the rectangle are equal to each other, we also know that AB equals to FP. Therefore, FP also must be equal to A. AB must be equal to A. AB must be equal to A. Here, in the next step, we'll prove that the green, but before that, we'll define angle LPS. This angle is theta. We'll focus on the right angle LSP. This angle equals to theta. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta. In order to complete the sum of the angles in this triangle to 180 degrees, this angle must be equal to 90 degrees minus theta. Again, 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. For the same reason, exactly, if we focus on the right triangle PFQ, this angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to 90 degrees minus theta. Okay. So in the next step, we'll prove that the green small right triangle LSP, this green small right triangle, is similar to the big right triangle QFP. Okay. The big right triangle FQP is similar to the small green right triangle LSP. Repeat again. The big right triangle FQP is similar to the small green right triangle LSP. So why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So I can write down that angle QFP this angle is equal to this angle, that is actually angle LSP. Both angles are equal to 90 degrees, therefore they are equal to each other. And repeat again, angle QPF equals QFP equals to angle LSP, is angle QFP equals to angle LSP equals to 90 degrees. In addition, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So this angle is FQP, and it is equal to this angle, that is actually angle SLP are equal to 90 degrees minus theta. I repeat again, angle FQP in the big right triangle equals to angle SLP in the small right green triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle that is equal to theta, it is a common angle that belongs to both triangles. So here, angle, so we can call this angle theta two different names. Okay, it is angle QPF. In this way, you can understand that it inside triangle QPF, and we can also call this angle theta angle SPL. Okay, SPL. I repeat again. Angle QPF equals to angle SPL. They are both equal. So angle theta equals to itself. It is a common angle that belongs to both triangles. So actually, we proved that the big right triangle FQP, FQP is similar, this is the sign of similar, to the small green right triangle LSP, according to angle similarity rule. Okay, and for the fact that the big right triangle is similar to the small green right triangle, we conclude that the following relationship exists between their sides. We conclude that FP in the big right triangle FP over SP in the small green triangle equals to QP over LP. Okay, I repeat again. From the fact that the big right triangle is similar to the small green right triangle, we conclude that FP over SP equals to QP over LP. So So here we have FP equals to A, according to what we have already found out, over SP. SP equals to 6 units, so we substitute SP by 6, and it is equal to QP. QP equals to 5 plus 6. Again, QP equals to 5 plus 6, that is 11. So we substitute QP by 11 over LP. LP, as I already mentioned here, it is the diameter of this circle that is equal to B. So we substitute LP by B. So in conclusion, I found out that according to question number 1, A over 6 equals to 11 over B. Here we cross multiply this equation number 1, and we get that according to equation number 1, A times B equals to 6 times 11 is 66. So I found out that A times B equals to 66, and according to our definition, AB equals to A and BC equals to B. Here you can see AB equals to A and BC equals to B, according to our definition. And the area of any rectangle, and especially rectangle ABCD, it is equal to the length of the rectangle, in this case is AB, times the width of the rectangle, in this case is BC. But AB equals to A according to our definition, BC equals to B according to our definition. So we found out that the area of the rectangle ABCD is A times B. We just right now found out that A times B is 66 square units. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. So in both methods we found out, we got to the same result, that the area of rectangle ABCD equals to 66 square units. So we finished with the first method. In the next step I will summarize the lecture. We'll start with the first question, of course. So in the drawing we have triangle ABC. Inside triangle ABC we have this circle. Actually this circle is inscribed by triangle ABC. This angle equals to 60 degrees, this angle equals to 75 degrees. Side BC equals to 2 units, and our mission is to find out the radius of this circle that is inscribed by triangle ABC. Okay, so we started with the first method here. From point C we draw perpendicular on AB. So then I copied triangle CDB that we created by the perpendicular, and we analyze triangle CBD. This is triangle CBD. Here this angle equals to 60 degrees, this angle equals to 90 degrees, and we know that the sum of the angles in any triangle is equal to 180 degrees. So in triangle BDC, which angles we have here? We have this angle that is 60 degrees plus this angle that is 90 degrees plus the missing angle. This is the missing angle that we define as angle X. In total, they must be equal to 180 degrees. 60 degrees plus 90 degrees is 150 degrees plus X must be equal to 80 degrees. We subtracted 150 degrees from this equation and we found out that the missing angle, angle x, this angle equals to 30 degrees. Okay, so we continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, sinus 30 degrees equals to BD over BC. Again, here sinus 30 degrees equals to BD over BC. Sinus 30 degrees is 1 over 2 is 1 half. So we substitute sinus 30 degrees by 1 half. And it is equal to BD over BC. BC equals to 2 units, therefore we substitute BC by 2 units. So we got here that 1 half equals to BD over 2. We multiply this equation by 2 and found out that BD equals to 1 unit. So here BD equals to 1 unit. We continue to focus on triangle BDC. In triangle BDC, cosine 30 degrees equals to BC, cosine 30 degrees equals to BD cosine 30 degrees. Here, cosine 30 degrees equals to BC cosine 30 degrees equals to DC over BC. Again, cosine 30 degrees equals to DC over BC. BC is the hypotenuse. Okay, so cosine 30 degrees is square root of 3 over 2. We substituted cosine 30 degrees by square root of 3 over 2. And it is equal to DC over BC, but BC is 2, so we substitute BC by 2. So we got that square root of 3 over 2 equals to DC over 2. We multiplied this equation by 2 and found out that DC equals to square root of 3. Here, DC equals to square root of 3. Then we focused on triangle ACD. First of all, we found out the size of this angle, angle ACD. What is the size of angle ACD? It is very simple to see from the drawing that the size of angle ACD equals to the size of angle ACB minus angle DCB. Angle ACB minus angle DCB will give us the size of this angle, angle ACD. Okay? So angle ACB equals to 75 degrees. Angle DCB equals to 30 degrees. Therefore, 75 degrees minus 30 degrees equals to 45 degrees. So actually found out that angle ACD equals to 45 degrees. So I copied triangle ACD in the new page and we analyze triangle ACD. This is triangle ACD that I copied from the original drawing. We know that this angle ACD, this angle ACD equals to 45 degrees, this angle equals to 90 degrees, and this is the missing angle, angle X. And we know that the sum of the angles in any triangle equals to 180 degrees, so here 45 degrees plus 90 degrees plus the size of this angle, that is angle X, in total they must be equal to 180 degrees. 45 degrees plus 90 degrees is 145 degrees, plus X is 180 degrees. So here we substituted 145 degrees for this equation and found out that the missing angle, angle X, equals to 45 degrees. So this angle equals to 45 degrees. Then I copied triangle ACD here, and we have here those two angles, they are equal to each other. They are all equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal sides. So in front of this angle, we have side DC. In front of this angle, we have side AD. And side AD must be equal to side AD according to the rule that I mentioned. Those two sides are located in front of equal angles, therefore they are equal to each other. But we have already found out that side DC equals to square root of 3 units. So from this equation, AD equals to DC equals to square root of 3 units, we will derive that side AD is also equal to 3 units. Side AD is also equal to 3 units, so I copied the right triangle ADC in this page and here, and we implemented the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC square. It must be equal to AD square plus DC square. AD square plus DC square equals to AC square. AD is square root of 3, so therefore AD square is square root of 3 squared, that is 3, and plus DC square, it is also square root of 3, therefore square root of 3 square is 3. So we found out that AC square equals to 3 plus 3. 3 plus 3 is 6, so AC square equals to 6. We took out of this equation, and we found out that AC equals to square root of 6. Square root of 6. Here, AC equals to square root of 6. Then I presented to you a new formula to find out the radius of any circle that is described by a triangle. The radius of the circle that is described by a triangle equals to the area of the triangle that blocks the circle over the semi-perimeter of the same triangle. So the radius of this circle that is inscribed by triangle ABC will be equal to the area of triangle ABC over the semi-perimeter of triangle ABC, that is the perimeter over 2. The area of triangle ABC, or the area of any triangle, is the base of the triangle times the height over 2. We choose AB as the base of triangle ABC. So AB is the base. The height of the base is CD because it creates 90 degrees with the base. So the base times the height over 2 is the area of triangle ABC. The base is AB. The height of the base is DC. And when you divide it by 2, we get the area. AB equals to 1 plus square root of 3. DC equals to square root of 3. And when you divide it by 2, we get the area of triangle ABC. Here we open the brackets. 1 times square root of 3 is square root of 3. Square root of 3 times square root of 3 is 3 over 2. So if we found out that the area of triangle ABC equals to 2.366. The semi-perimeter of triangle ABC equals to the sum of its sides lengths over 2. AB is 1 plus square root of 3 units in its length, BC is 2 units in its length, and AC is square root of 6 units in its length. So here, all divided by 2 in the semi-perimeter, that is 3.59. Therefore, the radius of the circle that is described by triangle ABC equals to the area of triangle ABC, that is 2.366 square units over the semi-perimeter of triangle ABC, that is 3.59, and 2.366 over 3.59 is 0.6589 units. So we found out that the radius of this circle that is described by triangle ABC is equal to 0.6589 units. We finished with the first method. Then I presented to you how to find out the area, how to find out the radius of the circle that is described by triangle ABC according to the second method. In the second method, we use two rules, rule number 1 and rule number 2. We actually proved that the green triangle is congruent to the orange triangle according to side rule, and therefore those two angles are equal to each other. The sum of those two angles is 60 degrees, and they are equal to each other, therefore each must be equal to 30 degrees. And here also we proved that the yellow triangle is congruent to the orange triangle, and the sum of those two, and therefore those two angles must be equal to each other. If the sum of those two angles is 75 degrees, it means that each of them must be equal to half of it. This is 75 over 2 is 37.5 units. Then we tangents, we focus on the green triangle. The green triangle tangents 30 degrees equals to R over BD. Okay. And in the yellow triangle, tangents 37.5 degrees equals to OD over DC. From this equation, we found out that BD equals to R over tangents 30 degrees. From this equation, we found out that DC equals to R over tangents 30 degrees. You can see, it is very easy to see that BC equals to BD plus DC. Here, BC equals to BD plus DC. We have the value of BD and we have also the value of DC. BC equals to 2 units, so now we have only one variable that is missing, that is R. And found out, according to the second method, that R equals to 0.658 units. As I already mentioned before, we relied on the first two rules, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency, and the lengths of two tangents from a common standpoint to a circle are equal. Okay, then I presented to you the second question, and we solved the second question in two different methods. Here we have rectangle ABCD. In rectangle ABCD, we have a circle that is inscribed by the rectangle ABCD, and our mission is to find out the area of this circle. Okay, so here we used the rule that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. For this reason, this angle equals 90 degrees, this angle equals 90 degrees. And we also know that all the angles inside the rectangle are right angles, so those four angles are right angles. In this way, we created the quadrilateral that has three right angles, and therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Then from point Q, we do perpendicular on BC, and here also we created quadrilateral with three right angles, therefore the fourth angle must be also equal to 90 degrees, therefore any quadrilateral that has four right angles must be at least a rectangle, if not a square. So OPGH is a rectangle, and we know that the opposite sides of a rectangle are parallel to each other, therefore OP is parallel to GH. But if OP is parallel to GH, OP must be parallel also to QH, because GH is part of QH. Okay, so OP is parallel to QH, and we have the rule that alternating angles between parallel lines are equal to each other. That is to say, those two angles that are located between the parallel lines OP and QH must be equal to each other. So if one angle is theta, then the other angle must be also equal to theta. Then we actually created two equations when we focus on the green triangle and on the big triangle PQH. And then we created equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Okay, it means that 6 over b must be equal to a over 11, therefore found out from this equation number 3 that the area of triangle ABCD is equal to 66 square units. Then I presented to you the second method. In the second method, we actually from point we join point P and O together by straight line. PO is the radius. We extended PO until it touches the side of rectangle ABCD at point F, and here BAB FP is a rectangle, and FPDC is also a rectangle, and the opposite sides of rectangle are equal to each other. Therefore, PF equals to A. And we actually proved that the green right triangle LSP is similar to the big right triangle FQP. And from the fact that those two triangles are similar to each other, we derived that FP over SP equals to QP over LP. FP equals to A, SP equals to 6, SP equals to 6, QP equals to 11, and LP equals to B. Of course, multiply this equation number 1, and we found out that AB equals to 66 square units. So in both methods, we found out that the area of triangle ABC, of rectangle ABCD, is equal to 66 square units. This is in the second question, and in the first question, we found in both methods that the radius of the circle that is described by triangle ABC is equal to 0.6589 units. Okay. Thank you very much.